Hi, good afternoon, everybody. And let me just say we're going to be starting in a couple of minutes' time. Okay. So this is the Turing Lecture, Provably Beneficial AI, given by Stuart Russell. Let's give it a couple more minutes. Hello and good afternoon, everybody. Welcome to this Turing Lecture. So the title of the lecture is Provably Beneficial AI. It will be given by Stuart Russell. My name is Chris Williams from the University of Edinburgh and a Turing Fellow. Just have a few sort of housekeeping announcements and then introduction of Stuart before we get started. Yes, welcome to this lecture. We, of course, had intended to give this lecture in late March as part of the AI UK event, but unfortunately, because of the pandemic, that didn't happen. And we're very pleased that Stuart can join us this afternoon for the lecture. So the Turing Lectures are the Institute's flagship lecture series, which have been running since 2016. And we're delighted to be able to continue the series despite the difficult times. There are a few housekeeping issues. Let's see if I can. I have to get the next slide up. Yes, okay. So there is closed captioning. So if you can't see the subtitles and you'd like to, you need to click on the closed caption button on the bottom toolbar of your screen. And the other issue is around questions. So there is a Q&A button in the Zoom, and we'll be taking questions through that mechanism. We'll have some question time at the end of the lecture. It's also possible to ask questions on Twitter with these two hashtags, Turing Lecture or Beneficial AI. But I have maybe a slight request. If you can use the Q&A, that may be easier for us to keep track of everything. Okay, so I think that's where we are in terms of the housekeeping. We will be recording this lecture and it will be hosted on YouTube after the event. So if you need to log off early for any reason, you'll be able to catch up later. So that's the housekeeping details. Then secondly, just introducing Stuart. So it's a great pleasure to introduce Stuart. He did his he read physics at Oxford for his BA and then obtained his PhD in computer science from Stanford in 1986. He's internationally renowned for his work in many areas of AI and for the textbook AI, A Modern Approach with Peter Norvig, which is the standard text on AI internationally. Stuart has received many honors, including the IJCAI Computers and Thought Award, the Feigenbaum Prize for the Association for the Advancement of Science, of Artificial Intelligence, and outstanding educator awards from both ACM and AAAI. He served as vice chair of the World Economic Forum's Council on AI and Robotics, and there's a long list of other honors which I won't go into here, so I don't eat into his time. But on reading his new book, Human Compatible AI and the Problem of Control, it reminded me again of the great breadth of Stuart's knowledge, not only in AI and computer science, but also in economics, philosophy, and social sciences. And thus it gives me great pleasure to ask Professor Russell to give his Turing lecture on provably beneficial AI. Thank you. So I'll just unshare this this slide and allow Stuart to bring up his slides. Please go ahead, Stuart. Stuart, I'm not getting any audio from you. I hope.
You should be getting audio now. Good.
Yes.
Okay. All right. So I'm very sorry that I couldn't be there in person. But it's very nice to be with you all virtually. So today I'm going to talk about artificial intelligence. And since it is the Turing Lecture, let me begin with a quote from Alan Turing. It seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So Alan said this in a lecture in 1951 on BBC, and there's no let out here. The tone of this paragraph is very much one of resignation. I hope we don't have to resign ourselves to this future. So the talk is going to be about what's going on in AI and what we could do about it in the future. So here's an example of what's going on in AI. You're probably more familiar with the computer vision algorithms that are able to recognize objects in the ImageNet dataset, or AlphaGo, which is able to play Go and beat the human world champion. But actually, I think this is another very impressive example. This is from OpenAI. And these are two humanoid simulated robots. So it doesn't look as good as, you know, the FIFA video game, but these robots this morning were newborn babies, in the sense that they woke up with absolutely no motor control abilities of any kind. All they could do was lie on the ground and shiver in random directions. And within a few hours, they learned to play football with each other and to score goals. The goalie is probably not the best, but the attacker seems actually to be quite competent at this game. So when you look at this, and of course, if you had newborn twins and in the afternoon that they were born, they were playing football in the garden like this, you would call in the priest to have an exorcism. So this kind of example has led people to think that possibly super intelligent AI is around the corner. So I actually don't believe that. And one of the reasons is that not all is what it seems. So if we take the blue player and we leave his program unchanged, and we just change the red player, can we get the blue player to score less often? Because at the moment, the blue player is winning this game quite significantly. So here's a different red program. It consists of falling on the floor and waggling his leg in the air. And now the same blue program is completely unable to play the game at all. Occasionally he scores almost by accident. Occasionally he manages to get the goal. Most of the time he just falls over. So what's going on here? What's going on actually is that the two players had not learned to play football. They had learned to do something else that looked like football, but in fact is not. And the blue player can only play as long as the red player is doing what he expects the red player to do. And otherwise, the blue player hasn't a clue. So he's not actually trying to kick the ball into the goal. He's more or less doing a dance with the red player. And when the red player stops dancing, the blue player has no idea what to do. So I think what's going on in AI is certainly significant progress, but also significant overinterpretation of what's really happening. And this kind of what we call adversarial example actually happens in many of the other areas, including computer vision, speech recognition, driving. we can come up with inputs that cause the system to fail in these sort of catastrophic ways. So I think we have a long way to go in machine learning. And a similar point was made by Francois Chollet. Francois is author of one of the most widely used deep learning toolkits, and he wrote a very well-regarded textbook on deep learning. And this is what he said at the end of the book: many more applications are completely out of reach for current deep learning techniques, even given vast amounts of human annotated data. And he went on to say that the main directions in which I see promise are models closer to general purpose computer programs. And the reason for this is that current deep learning systems are basically circuits. They're enormous tunable circuits. And no one has actually used circuits for computing since before the Second World War. As soon as we understood and built general purpose computer programmable devices, then we realized that wiring up circuits to do specific computations was an extremely painful and limited and inexpressive way of doing computation. So it turns out there is another area of AI separate from deep learning called parabolic programming. And so what Francois Chollet hoped we might be able to do has actually been going on now for more than 20 years. In parabolic programming, what we do is we connect up probability theory with one of two roughly equally expressive formalisms. One is called first order logic, which goes back at least to the 19th century. And the other one is ordinary general purpose programming languages. So when you combine probability theory with one of these two things, you get the ability to write down models of the world in a language that's as expressive as possible, in the sense it's as expressive as Turing machines, which means that any other language that you could come up with is going to be roughly the same, in the sense that you can always translate between one language and the other without some enormous blow-up. And along with these languages, we also have general purpose reasoning and learning algorithms. So that means we can take whatever knowledge we have, express it in this formalism, combine it with data, and then make predictions or make decisions. So parabolic programming is actually a little stealth discipline that's been growing very rapidly. This shows the number of papers published per year in parabolic programming. So starting around 2008, and by 2019, reaching about 2,000 papers a year. So I think in the future, what we'll see is probably some kind of merger between parabolic programming and deep learning, and that will fuel the next phase of growth in AI. Let me give you one quick example of a parabolic program in operation. So this map shows the sordid history of testing of nuclear weapons. And I was sorry to hear that just a couple of days ago, the US administration raised the idea that it might restart nuclear testing. We've been trying now for about 60 years to get rid of nuclear testing. One of the reasons is that nuclear testing killed about 100,000 people through radiation caused by fallout from the tests. And this map shows all the locations of the testing facilities. And here's a picture of one small test. This is the crater left by a test in Nevada. This small test dumped 12 million tons of radioactive earth and rock into the atmosphere. The largest test was about 500 times bigger than this one. So the treaty that bans nuclear testing is called the CTBT, the Comprehensive Nuclear Test Ban Treaty. And the verification arm of that is based primarily on a global seismic monitoring network. So we collect evidence from about 150 seismic stations scattered all over the world. Those stations produce data that looks like this, so the classical sort of wiggly line drawn by the earthquake sensors, except these are electronic sensors that detect movements down to 1 nanometer in the earth. the question we would like to answer is what happened? What happened today? What are all the events that took place? Where did they take place? How deep were they? How big were they? And we call this the bulletin, the daily bulletin. And this daily bulletin, all those red dots are seismic events. This shows actually a 3-month summary bulletin. The information we have about the problem is the geophysics of the Earth. So the natural seismicity, and then when an event happens, how does that signal propagate? What kinds of signals, what path do those signals take? What's the probability of detection? What's the rate of noise at each of the stations, and so on. So this is the basic background knowledge we have about the problem. We combine that model with all of the data, the evidence from the 150 stations, and then we ask the query what happened, and then the probabilistic inference algorithm does the work to answer the question. And so that algorithm is, in effect, the global monitoring system for the treaty. So here's the model written in one of these probabilistic programming languages. I'm not going to go through it line by line, but just to point out that, in fact, it's very concise. It's extremely natural. So I could take any seismologist or geophysicist and walk them through this line by line, and they would instantly understand and probably be able to improve the model in a very straightforward way. So this is the model. The data comes from the stations. The inference algorithm runs and produces answers. And what we're trying to do is to reduce the detection failure rate of the overall system. So the existing system, which costs about $1 billion for the hardware and about $100 million for the software, and about 100 years of research in seismology, fails between 30 and 50% of the time. And within about 9 months of starting work on this problem, of learning even what the problem was, we were able to use that model that I just showed you to reduce the error rate by a factor of almost 3. It took 7 years to get through all the committees at the United Nations, and it was switched on at the beginning of 2018 officially, although it had been running all the time in the headquarters at Vienna. So it was running in 2013 when North Korea did a test. And this is a satellite image of the area of North Korea where the test took place. This is the consensus location of all the geophysics experts in the world. This is the real-time estimate from the algorithm as to where the event took place. And then this turns out, this was discovered later in satellite images, that this is the tunnel entrance to the testing facility. So we were about 700 meters away from the tunnel entrance using detectors that are 4,000 to 8,000 kilometers away. So what I'm not here to tell you is that super intelligent AI is right around the corner. In fact, I think there are major breakthroughs that still have to happen. We don't have systems that really understand language. We don't know how to accumulate knowledge over time and use that knowledge to improve the rate of learning, to discover new concepts and theories and so on. So these breakthroughs are extremely unpredictable. We cannot draw a graph with exponentially growing computation and predict a date at which machines will be as intelligent as human beings. And in fact, there probably won't be such a date, because machines, of course, already exceed human capabilities in some dimensions. And at some point, they will exceed human capabilities in all dimensions, but there'll be no time at which they're comparable to human beings. So just to illustrate how unpredictable these dates are, here's a quote from Lord Rutherford, who was giving a speech in Leicester in 1933 on September the 11th. And he was asked, is there any possibility that we could tap into atomic energy? So we knew since Einstein the quantities of energy available if we could cause nuclear transitions to take place was absolutely enormous. And they had accurate calculations of what a nuclear explosion would be like. But they had no idea how to make any such nuclear transition take place. And Rutherford said, it's moonshine. He didn't even think in 25 or 30 years' time it would be possible. And even Einstein said pretty much the same thing. So Leo Szilard read a report of this speech in the Times the next morning, and he went for a walk and invented the neutron-induced nuclear chain reaction. He patented nuclear reactor the following year and demonstrated one of these reactions 6 years later. And of course, we know what happened after that. So the problem went from completely impossible to essentially solved literally overnight. So we don't have a guarantee that these advances in AI won't happen overnight. It's very unlikely that they'll all happen overnight in one night, but any one of them could take place, and that would have a significant impact on the rate of progress in AI. So I think we have to work on the assumption that AI systems will eventually be able to make better decisions than humans can in the real world. So what I mean by this is that just as on the Go board, AI systems already make much better decisions than humans, partly because they're able to look further ahead into the future. They're going to be able to do the same thing in the real decisions that humans are making all the time in the actual world. They'll have access to much more information. They will be able to look further ahead. And that means that their decisions will be right much more often than the ones we make. The only alternative I see to this is to assume that at some point we fail to make further progress in AI. That could happen for other reasons, for example, a collapse of civilization, but assuming that civilization continues and the investments that are happening in AI are accelerating all the time, it seems pretty implausible to say that we're simply going to fail and therefore we don't need to worry about success. That's sort of like driving towards a cliff with the whole human race as passengers in your bus and saying, well, don't worry, I'm sure we're going to run out of gas before we fall off the cliff. It's just not very reassuring. And so that leads us back to Turing's point. We're going to create entities that are more powerful than us, but we have to retain control over them forever. There are not a lot of good precedents for how to do this. When I gave talks on this over the last few years, I used to include the counter arguments and then try to address each of those counter arguments in turn. It ended up that there were too many, and I think they were also too embarrassing to some of the protagonists. So I put a lot of them in a paper that I've cited here at the bottom. So let me talk about where I think things have gone wrong. If we're developing a technology that seems likely to lead to the end of the human era, and we're continuing to do it, something must be not quite right. So let's go back to the very beginning of AI. What does AI mean? And what I'm going to describe here is a little bit of a caricature, but it's actually fairly accurate caricature of pretty much all the research areas in artificial intelligence. So what happens in the standard model is that a human being specifies an objective. And here I've described it as the objective that we use in reinforcement learning. But the same thing would happen in logical planning if you gave a goal, or in search where you give a goal and a cost function, and so on. So in all of these different areas of AI, there's an objective that we specify, and then the machine is supposed to take this objective and go off and achieve it. So this is not just the standard model for AI. In control theory, we do the same thing. We specify a cost function, and then we derive a controller that minimizes that cost function. In statistics, it's a loss function. In operations research, it's a reward function that we maximize. In economics, it's a utility function or a welfare function or a quarterly profit that we maximize. So this standard model underlies a lot of what we did in the 20th century, and it's very important, very powerful, very successful. But I would like to argue that it's in fact wrong. And the reason is something that we've known for a long time. King Midas said that everything I touch should turn to gold, and so that was the objective that he put into the machine. And then, of course, when the machine carried out the objective, he could no longer eat or drink or even touch his family members without turning them into gold. And so he dies in misery and starvation. And every culture has the same basic legend that humans are not very good at specifying objectives correctly. And so when you specify an objective incorrectly and it's being carried out by a powerful entity, then that entity can mess up the rest of the world in order to achieve this incorrectly specified objective. And so the smarter the AI system, the worse the outcome is going to be when you specify the objective incorrectly. Let's give you a simple example. We're all familiar with how content selection algorithms work on social media. So think of YouTube as one example. So you watch a video and then it recommends a next video for you to watch. So what is it trying to do? Well, roughly speaking, the idea is to optimize click-through. So maximize the probability that you're going to click on whatever thing it recommends that you should read or watch. And you might think, okay, well, that's all right. I mean, in order to do that, it's going to have to learn what I like clicking on. And so it's going to send me things I'm interested in and not send me things that I find boring or repulsive. So is it learning what people want? No. What it's actually doing is modifying you to be more predictable. So it's training you to like to click on things that it can then send you to click on. And that means typically modifying your tastes, your opinions, your views in directions that are more narrow and possibly more extreme. So here we see a simple machine learning algorithm optimizing a simple and incorrectly specified objective that's having a very significant impact on the world. And most people would say in a negative direction. So how did we make this mistake? How do we come to adopt the standard model for AI where humans are trying to plug objectives into machines? So I think it began with the idea that in order to build AI, we first had to know what the I means. What do we mean by intelligence? And the notion that was understood by the 1940s, both by philosophers and economists, and fairly widely agreed on, was that intelligence, or certainly this notion of rationality, has to do with the ability to achieve objectives. So humans are intelligent to the extent that our actions can be expected to achieve our objectives. And then you just translate this to the machine. Machines are intelligent to the extent that their actions can be expected to achieve their objectives. Now, of course, the machines don't have objectives of their own, so we have to plug them in. And that's where the standard model comes from. And what I just argued is that this standard model is really a big mistake. And if you think about it, it's not really what we want. What we want is the following. We want machines whose actions can be expected to achieve our objectives. So their actions achieve our objectives. And this is obviously a more complicated problem because our objectives are in us and not in the machine. So that makes it difficult for them to achieve those objectives. But this is what we want. We don't want to force the human to try to make their own objectives explicit and plug them into the machine, at which point those objectives become the machine's objectives. Because that process, as we've seen, is extremely fragile and dangerous. So the new model is built on some different principles. So the robot has an implicit objective, which is to satisfy human preferences in general. And I put an asterisk on preferences to remind you that preferences here doesn't mean what kind of pizza you like or which bus you want to take, but it means your preferences about all possible futures. So how you want the future to unfold, how you would rank all the futures that could be imagined. But the important point is that the robot doesn't know what those preferences are. The connection between the human and the robot is made through human behavior. And in fact, if you think about it, other than perhaps modern tools like fMRI, which can sort of directly examine your brain to try to figure out what you like or what you want the future to be, the only evidence that we have or robots would have about human preferences is human behavior. So generally, the choices we make reveal information about what it is we want the future to be like. Obviously, that process is imperfect and complicated, and I'll talk more about that part later. We can take these simple principles and we can formulate a mathematical problem that we want the robot to solve. We call this problem an assistance game. So we want the robot to solve its half of this assistance game. And the idea is that when it solves its half of the assistance game, the better it solves it, the better the outcome is going to be, because it's going to more accurately learn about our preferences, and it's going to more successfully satisfy those preferences in future. So let me show you exactly how these, well, I'm not going to show you exactly how these games work because there's too much maths, but here's the basic principle. So here's the human, and the human has some preferences, and we'll use the Greek letter theta to represent those preferences. And we'll assume that the human acts roughly according to theta. It doesn't have to be perfect, but there has to be some connection between what you want and what you do. And here's the robot. And the robot's job is to maximize these unknown preferences. And the robot starts out not knowing what the preferences are, but perhaps has some prior belief, P of theta, some probability distribution over what the preferences theta might be. And there's a whole sequence of references there at the bottom showing these papers show exactly how to define these problems, how to set them up, how to solve them, what kinds of behaviors result. And when you look at the behaviors that result, what are the solutions of the game, or in game theory, what we call the equilibria of the game? It turns out that the human, when they're solving their half of this game, will naturally want to teach the robot so that the robot becomes useful. The human will want to essentially try to convey preferences to the robot in any way that's feasible. And the robot can learn, can understand the human's teaching actions, which might include saying out loud what the objective is, but of course the robot understands that that may not be a perfect statement of a true objective. And then the robot's also motivated to ask questions. It's motivated to ask permission before doing something drastic to the world, like changing the oceans into sulfuric acid as a way of curing global warming. It should ask, is this okay? Because I don't know your preferences for acidification of the oceans. I do know that you want to reduce carbon dioxide, but I'm not sure about the sulfuric acid. So you would want the robot to ask permission, and it will do that, not because we program it to do that, but because that's the solution of the game. That is the correct action to take when the robot is solving this kind of game. And the robot will defer to human instructions because the human is the source of the preferences that matter. And the robot will even allow itself to be switched off, as I'll show in a second. So what I'm arguing here is that historically we built up AI on this foundation of algorithms that are given a fixed known objective and then try to solve it. So just going through the chapters of the textbook, we have search algorithms, we have constraint satisfaction algorithms, planning algorithms, algorithms for solving Markov decision processes, which is planning under uncertainty, algorithms for learning, algorithms for perception, robotics, and so on. And all of these are based on this idea of a fixed known objective. And all of these have to be revised to allow for uncertainty about the objective. And crucially, when there's uncertainty about the objective, the key extra ingredient is that there's got to be some connection with the human who actually has the objectives, so the preferences. So to all of these algorithms, we add both uncertainty and some notion of interaction between the algorithm and the human in order for the whole process to work correctly. So let me give you a few simple examples. One of them is actually a pretty familiar example to most people in AI these days, the recognition of objects in images. So image classification, you take a photograph and you say, oh yeah, this is a bus or this is a dog. So the way that's typically done is to take a training set of images with their labels and then train a classifier which minimizes an expected loss. So the loss is the total cost of the errors that you would make with that classifier. We quantify the loss using what's called a loss matrix, which says for each category, what's the cost of mislabeling that category as a different category. So for example, what's the cost of taking an image that's of a dog and labeling it as a cat? And usually what happens in machine learning is that we assume this loss matrix is uniform. So every error is equally bad. And in fact, in most cases, people don't even think about what the loss matrix should be. They just plunge ahead with the assumption of equal cost. And then what happens is that you accidentally classify a human being as a gorilla in a very public way, and your error goes viral, and your company spends hundreds of millions of dollars on doing an emergency public relations disaster control effort. So if you said, well, okay, we should have specified the loss matrix up front, we should have written down up front that classifying a human as a gorilla is a very expensive mistake and so on. But unfortunately, there's 20,000 categories of objects that are labeled in the ImageNet data set. And so the matrix is 20,000 by 20,000, 400 million entries. And no one knows what those numbers should be. So there has to be uncertainty about the loss function. And we have to have algorithms that are sensitive to that uncertainty. So you might start out with a prior probability distribution over this enormous loss matrix. So that's a 400 million dimensional probability distribution. And we actually need to do a whole lot of new science just to figure out how to even describe such a prior probability distribution. And then we need new algorithms that can operate with this uncertainty. And in particular, those algorithms should do things like saying, I'm not going to classify this image because there's too much uncertainty about the cost of making an error. And I'm actually going to go back to the expert and ask for some more information about the relative merits of these kinds of errors. So these algorithms don't yet exist, but this is clearly an area that needs to be studied in much greater depth. Here's another example, right? Let's go the simple standard case where an AI lab gets a mobile robot. The first thing it seems that they do is they train it to either go to the Coke machine and get a Coca-Cola, or go to the coffee machine and get a coffee for the professor. This is sort of a rite of passage, a hazing ritual, if you like, for new robots in robotics labs. So what does fetch some coffee mean? Well, in the classical view, fetch some coffee becomes the objective. So now the robot's mission in life is to get this coffee. And that leads to all kinds of failure modes. If the machine was sufficiently intelligent, for example, it would realize that it can't fetch the coffee if it's dead, and so it will disable its own off switch so that no one can interfere with the mission of fetching the coffee. It would barge people aside, possibly electrocute them if they were getting in the way at the coffee shop, and so on and so forth. But now we're going to say, okay, the robot is actually going to be uncertain. It's not going to adopt this as its sole life's mission. It understands that there's lots of other things that the human might care about. So we actually need to understand this command in a very different way. And one way to understand it is to say that the coffee is essentially preferable to no coffee all other things being equal, or in Latin, caeteris paribus. And that meaning for the instruction essentially says that there's a little, basically a little local gradient information for the human's preference landscape, if you like. And that's all it is. It doesn't say anything about your preferences for other things. So then the question is, well, if that's all you know, and the human might have all kinds of preferences about all kinds of other stuff, how on earth is the robot going to act at all? And the answer is, of course, that if the robot can fetch the coffee without messing up anything else, then it's a good idea to fetch the coffee. So it motivates this idea of minimally invasive behavior. So don't mess with attributes if the value of those attributes is uncertain. Just act within the subset of the world that you actually understand well enough to act. And in fact, there's a further justification, and the paper here is from iClear 2019. There's a further justification, which is that the world is already in a state that we kind of like, right? We have been acting on this world for thousands of years now. And so you could think of the world not as a random world, but as a world that's already the result of rational agents acting on it for thousands of years. And so that gives you a reason not to mess with it. Another interesting example of actions that the robots can take, even when it has massive uncertainty about human preferences, is an action that expands the choice set for the human being, right? So if, for example, if you've forgotten your password, the robot can find out your password and give it to you, because that expands the choices that you now have. Now you're able to do something that you couldn't do before. So no matter what your preferences are, simply expanding the set of actions for the human is guaranteed to be non-negative benefit to you. And so there's actually quite a lot the robot can do, even when it has radical amount of uncertainty about your preferences. So I'm going to show you one very simple game here, an example of one of these assistance games. This is the simplest one we could come up with. And in a sense, it has a kind of a one-dimensional state space. So imagine that the robot can make paper clips or staples. And human beings have preferences about paper clips and staples. Some people like paper clips, and some people like staples, and some people are indifferent. And so here, the human preferences, the theta variable, is basically like an exchange rate. So we're going to say that the human reward for the state with P paper clips and S staples is theta times P plus 1 minus theta times S. So let's say that theta is 0.49. You can think that's 49p. So that means that paper clips are worth 49p and staples are worth 51p. And initially, the robot has no idea what the human preference between these two things are. And so the exchange rate theta could be anywhere between 0 and 1. Now, the way we set this particular game up is that the human gets to go first, and the human can choose to either make 2 paper clips and no staples, 1 of each, or no paper clips and 2 staples. And if that was the end of the game, of course, then it's very easy to see that if the human prefers staples, the 51p versus 49, then these would be the values of those choices. And the human would clearly choose to make 2 staples because they have a slight preference for staples over paper clips. But the second round of the game, the robot is going to do some sort of mass manufacturing. So it can make either 90 paper clips or 50 of each, or 90 staples. So the question is, what should the robot do and what should the human do? Well, what the human is going to do depends on what the robot's going to do. In some sense here, what has to happen is that the human has to make a choice that's informative to the robot about what the human wants. And then the robot has to infer from the human choice what it is that the human wants, and then choose its behavior accordingly. So we have a kind of circle here that what the robot does depends on what the human intends, and what the human intends depends on what the robot's going to do. We solve those kinds of circles by solving for the equilibrium of the game. And when you solve the game, you find out that, that making one of each is optimal for a preference theta that's anywhere in the range from 44.6p to 55.4p. So if the human is sort of in the middle, like fairly indifferent between paperclips and staples, then making one of each is the right answer. And in response, the robot will then make 50 of each. So the human decision here, making 2, 0, 1, 1, or 0, 2, is encoding information about human preferences. And that code is discovered by solving the game. And then that solution tells you how to code your preferences in the optimal way. Okay, let me show you now how it is that these kinds of AI systems are able to let us switch them off. So here's the robot in our lab, the PR2. It's a pretty hefty robot. It weighs about 400 pounds. And like any large robot, it's legally required to have an off switch on the back. And there's the off switch. And it's there for emergencies if something is going wrong. So remember what happens when you ask the robot to fetch the coffee. The robot, at least if it's sufficiently intelligent, immediately says, well, I can't fetch the coffee if I'm dead. So I'm going to disable my off switch. And that's an important first step in any plan to fetch the coffee. No, we don't want this to happen, right? We want to retain control. In fact, in another lecture, Alan Turing said, well, perhaps we might be able to switch them off if we're lucky. So this is the essence of the idea of retaining control over robots. If you can't switch them off, then really the game is over. And what I'm going to show you is that when you have uncertainty, or when the robot has uncertainty about the objective, it won't do this. It won't disable its off switch. So again, we set it up as a simple game, just to illustrate the idea. In this game, the robot gets to go first. And imagine that the robot has two choices here. One is a big red button that it could push. And the robot's not sure if this big red button is a good idea to push. You know, perhaps it starts the sprinklers in the building, perhaps it starts a nuclear war, or you know, perhaps it sets off the burglar alarm, or perhaps it does something useful. The alternative the robot has would be to switch itself off. And we're going to fix the utility of switching itself off at 0 from the point of view of the human being. And then the robot is uncertain about the value of this other action, pushing the big red button. And so I've illustrated that on the left with this probability distribution, saying the robot has a lot of uncertainty about the value. So the value is on the x-axis. And if that was the robot's only information and only option, because this distribution is a little bit positive, so it's slightly better than just switching yourself off or committing suicide, the robot will go ahead and push the big red button. And that's something we would possibly like to avoid. We want to be able to switch the robot off and have control. So we're going to give the robot another choice, which is to wait and allow the human to switch the robot off. So now the human could switch the robot off, and that would have value 0, or the human can say to the robot, just go ahead. Now you might ask, well, what's the point of this, right? If the only thing the human can do is switch the robot off, and the robot could do that already itself, what does it gain from waiting and letting the human do it? And the answer is that when the human does it or doesn't do it, the robot is in some sense gaining information about the human preference function, right? And in fact, what it's really saying is, well, the human's going to switch me off if the other thing I was going to do, which is push the big red button, is actually extremely bad, okay? And so by learning that the human hasn't switched me off, then the robot knows that this action of pushing the big red button is not extremely bad. In fact, the negative quadrant of the distribution disappears, and now the robot knows that it's fine to go ahead and push the big red button. When you calculate the expected value to the robot of waiting, you find that it's always non-negative compared to the options that it has already. And so the robot is always incentivized to allow the human to switch it off. And that incentive, it turns out, is directly related to the amount of uncertainty over the value of pushing the big red button. So uncertainty about preferences is intimately connected to the safety of the robots we build. We can also show that when the robot is designed this way, it's going to be provably beneficial to the human. And in fact, in this example, you can see that this is trivially true because the only thing the robot's going to end up doing is something that we approve of. If the action it was going to do is bad, then we're going to switch it off, which has value 0. And if the action it was going to do is good, then it's good. And so the only two options are non-negative. So there's a lot more research to be done. And many of you are writing questions, and I imagine you're thinking about some of these research directions already. So the first set of
5-minute warning, sorry.
Yep. So the first set of directions has to do with imperfection in human behavior. So this connection between our preferences and the behavior, which is supposed to be revealing those preferences. If that connection is imperfect, which it inevitably is, then inverting that connection, sort of reverse engineering human behavior to get at our underlying preferences is going to be a very non-trivial process. And so here are some of the ways in which our behavior is imperfect. Probably the most important one actually is, the most important one is the plasticity of preferences. So when humans have preferences that can be molded by external influences, then we actually have an additional failure mode, which is that the machine satisfies your preferences by changing your preferences to be easy to satisfy. And so this is something that philosophers are just beginning to struggle with. They've been aware of the issue for a long time, but actual solutions for how you even think about decision-making with changing preferences is fairly new. The other area is, of course, many humans. So there isn't just one human, as I showed you in the assistance game. There's a lot of humans. And these questions about how do you make decisions on behalf of many humans have been studied in political science and social science and moral philosophy for literally thousands of years. And some of those questions actually become a little bit easier here because the decision-making in question is made by a robot that has no preferences of its own. So there's no issue of trading the robot's preferences against those of the humans. But there's still a question of how we trade off the preferences of the humans because we can't satisfy them all perfectly. How do we deal with what we call interpersonal comparisons of preferences? So how do we even measure, how important or intense one person's preferences are relative to another person's? How do we ensure that the human beings are honest in the information they provide about their preferences? So that's a problem that we call mechanism design in economics, incentive compatibility, and so on. So lots of very interesting research questions. Here's just one of them. How should a robot aggregate human preferences? So there's a theorem due to John Hassani, who was a Berkeley professor and Nobel Prize winner. And he showed that all Pareto optimal policies, so that means policies that are acceptable to everyone, have to optimize a linear combination of the individual preferences of people. And this theorem assumes a common prior about the future. So everyone has to have the same beliefs about what's going to happen in future in order for this theorem to go through. And we wondered, okay, could we relax that assumption? Because of course, people don't have the same beliefs. And we got a pretty shocking result, which is that all optimal policies have weights that are proportional to how well each person predicts the future. And initially, we were quite disturbed about this because, in fact, the weights could even become exponentially disproportionate to each other. So why is it that this is the answer? And the answer, of course, is that everyone loves this policy because everyone thinks that they're the ones who are right about the future and everyone else is wrong. Because, of course, you have to believe your own beliefs. You don't believe that your own beliefs are wrong. You believe your own beliefs. And so this is the policy you prefer compared to the one with fixed weights, which doesn't reward you for being right. So everyone loves this policy. even though it seems to be very, very inegalitarian. So the social consequences we don't know yet, but this is a theorem and we have to deal with its consequences. I think I'm going to skip over altruism, indifference, and sadism, just to point out that the issue that some of you may be thinking about, well, what about the preferences of people who are sadists, who actually want to hurt other people? This is an old issue, and Harsanyi simply points out that we should ignore those sadistic preferences. So if your sort of caring coefficient, how much Alice cares about Bob, if that's negative, then we should ignore that coefficient in Alice's preferences. And then it's worth pointing out that actually an enormous amount of our preferences about the world are effectively sadistic. You may be a bit shocked to hear that, but it's because our preferences are relative. So our relative preferences means that we include in our well-being a notion of, or in our utility function, a notion of envy and pride. We have envy because other people's well-being is higher, and we have pride because other people's well-being is lower. And both of those terms end up being negative factors with respect to other people's well-being, because you don't like it, and the less they have, the more pride you feel. And so they work mathematically just like sadism, and it's a much more important question. Should we zero out relative preferences, relative well-being, what we call positional goods in economics, because so much of our preferences are actually functioning that way. So to wrap it up, if you're interested in more details, there's a book for a general audience called Human Compatible, which Chris mentioned at the beginning, and that came out last October. And then just recently, we finished the 4th edition of the textbook, which has some of the same information in more technical forms. So to summarize, we can actually build AI that is provably beneficial to human beings, even though that sounds like a bit of an oxymoron. It's not just possible, it's desirable. It's the right kind of AI to build, and for obvious reasons, not just about safety or ethics, but it's the right kind of AI. And I want to get away from this idea that there's an AI community and a separate AI ethics community that is wagging their finger at the AI community and telling them that they're bad people. We don't worry about bridge designers who deliberately build bridges that fall down. It's just intrinsic in the meaning of the word bridge that it's not supposed to fall down, and that's what civil engineers do. And it should be the same with AI. We should say, look, if it's not going to be beneficial to humans, it's just a bad kind of AI. So there's lots of interesting research to do, and I won't go into that, but I have to take questions about it. I want to point out that there's 2 other problems that I haven't addressed at all. So one we might call the Dr. Evil problem, which is that even if you have safe, beneficial AI, why does Dr. Evil care? He wants to use the AI that lets him take over the world. And that's a policing problem, if you like. And then the other problem is one of not misuse, but overuse. There's a picture from Wall-E where humans have been enfeebled because machines have taken over the running of civilization. So they manage everything, and humans then no longer need to understand anything. They no longer need to learn. And this kind of enfeeblement, I think, is a serious question for our society, more of a cultural question than a technological question. So with that, I will say thank you and happy to take questions.
Okay, thank you, Stuart. Thank you for a very thought-provoking lecture now. I have a very difficult problem. I have lots of questions that are coming in, and it's quite hard to make choices about these, but let me try to pick up 1 or 2 from things that you've said. One is from Jeremy Isaacs here. It says, how do we control unethical preferences that can become the consensus at a point of time? So your final slide talked about AI safety and AI ethics. So maybe it would be nice to sort of, could you expand on how such a system that's doing this, acting beneficially, will actually avoid such unethical preferences or perhaps other risks of bias in decision making and so on? How does that unfold from your formulation?
Yeah. So let me start with the last thing first. So bias is a good example, and we in the last few years, AI researchers and others have become aware that machine learning systems can produce very biased results. It could be gender bias, racial bias, and so on. Not because there's something biased about the algorithm per se, but because the underlying data sets are produced by a very biased society. And sometimes the algorithms actually amplify the bias. And I think that this is a clear example, again, of misspecifying the objective, because when we apply those algorithms, we're typically minimizing least squared error, which sounds like a very neutral objective. But you have to ask, well, what's the consequence of minimizing least squared error and then deploying the result in reality? And I think if you ask the question that way, then you would start to think about, okay, what are the consequences of decisions, and what, the least squares means least squares with respect to the training data. And so then you have to ask, is the training data already biased? Is it fair? Now, working back to the first part of the question. So in human compatible, I give this example of a passport official who is taking bribes, insisting that you have to give him a bribe for every passport transaction you'd like to exercise. And the question is, well, is the machine going to learn bad behavior by watching these bad people? And the answer is no, not really, and no more than a criminologist becomes a criminal simply because they observe criminal behavior. In fact, what the criminologist does is to try to understand why the criminals are doing what they're doing. So the AI system here is learning what are the underlying preferences of that individual, but not learning to actually carry out the same kinds of actions as the individual, because of course the AI system understands that other people, including the people who need passports, have preferences. And the passport official might be doing it because they want to send their children to school, and school is expensive and the government salary is pathetic. In fact, in many countries, the government salary assumes that you're going to take bribes. And so the system is understanding why the passport official is doing this, and will perhaps find some other way to help them send their children to school that doesn't have all the negative effects on lots of other people. So unethical actions are a combination of preferences that may have too little weight on the well-being of others, but they're the result of preferences of the individual and the circumstances that occur in the world. The AI system, of course, doesn't have any of its own preferences, and so it doesn't act selfishly at all. And it takes into account the preferences of everybody, and so should not be responding to unethical preferences in that way.
Okay, thank you. I have one other question here from Ghazi Ahmad. It says, thank you for your fantastic lecture. My question is, won't this level of indecision mean that these AI systems would spend their whole time just asking clarifying questions of a human, thinking of an AI assistant that asks so many questions that the human might as well do it themselves? So is this a problem that might arise?
Yeah, so this is a very good question, and I mean, in some sense, you can't help it, right? I mean, if you shouldn't build, if you build an AI system that really doesn't know what the hell it's doing, then you would want it to be asking questions, because you wouldn't want to be doing anything at all. So there is a cost, of course, for answering questions, and the AI system would take that into account. And so when there's an action it can take that has a very low risk of negative consequences and a decent probability of a positive outcome, then it might well choose not to ask. But for anything more serious, you would want it to ask. And then gradually it will learn. And don't forget, we are all pretty similar. So it's not as if every AI system is going to come out of the box not knowing anything about human beings at all, right? Just as if we had sent the AI system off, to another star system and it's supposed to serve an alien that we know nothing about. It will come, and companies will start up to actually build models of human preferences and even models of the typical preferences of different types of people. But of course, those will only be prior probability distributions. They won't be set in stone. And so, even if it thinks that, I'm a typical California vegetarian, which I'm not, it might believe that out of the box, but come to realize that actually, no, I'm eating roast whale for dinner, so I'm not the typical Green Party member. In the long run, the approach I'm suggesting here is actually strictly a generalization of the way we do AI now. So the way we do AI now is that we plug in this objective, and that plugging in, that stating of what the objective is just a special case where the robot starts out with complete certainty about the objective. But we understood actually since the early 80s in AI, and since much earlier in control theory and other disciplines, that perfect certainty about the world is rarely a reasonable attitude. So we've always had uncertainty about the dynamics of the world or the transition model. We know that our sensors produce uncertain or noisy or partial information. And for some reason, we just had this blind spot that nonetheless, despite all that uncertainty, there's perfect certainty about the objective. I don't really understand why, and it's clearly a mistake, and we just have to rectify it.
Thank you. Let me ask one final question from the chat here. I'm sorry to everybody. There's, sort of 40 odd questions, and I'm afraid we clearly can't address them all. So there's one here from Markov Kolbeit, and it says, we cannot write secure programs of any scale, so how can we hope to build provably beneficial AI correctly?
That's a great question. And I think it's somewhat orthogonal to the directions that I'm talking about, but I would argue that actually we can build secure programs at scale. It's just much more expensive. I mean, we have built provably correct Linux kernels, for example. So the scale is already in the hundreds of thousands or small millions of lines of code in terms of verification. But I would say that much more is needed in that direction just for our regular software infrastructure on which the world relies. And I think of this as sort of complementary activity. The thing that we're doing about provably beneficial AI is actually the structures are relatively simple. If you want to think about it in sort of box and arrow diagrams, it's a relatively small number of boxes and feedback loops and inputs and comparisons and so on. And we show that box and arrow diagram is provably beneficial on the assumption that each box is correctly implemented to do what it does. It's certainly the case that that AI systems will be subject to cybercrime attacks and all that kind of thing. And I think we're going to need, just as I talked about the misuse case, the Dr. Evil problem, we're going to need much more serious policing, international agreements, standards, verification, program checking, as these AI systems become more powerful. In fact, I would argue that for ordinary software systems, we are far behind where we should be. And that's why cybercrime is already $1 trillion a year problem. But I'm reasonably optimistic that that problem can be kept under control.
Okay, lovely. So I think in the interest of time, we should stop here, and let's thank Stuart for an excellent talk and these questions. I'm afraid you can't hear the virtual applause, but I think you might be able to see it. It'll arise. There's some emojis or things that can be used for that. So yes, thanks very much, Stuart, and for a fascinating lecture. And as I say, I'm sorry to everybody that we just can't address all your questions here. Before we close, I'd like to thank the events team at the Turing for their work on setting this up, and also to let everybody know that actually the Turing's next virtual event is on Thursday. It's called Countering COVID-19 with Technology and Trust. And it's a live webinar with panelists, including Dr. Simon Eccles, the Deputy CEO of NHSX. We'll be discussing key challenges in relation to collection and analysis of data as a public health intervention in COVID-19. So there are many interesting talks and events happening through Turing. And so, yeah, but again, thank you to Stuart. Okay, good night, goodbye, everybody.
Goodbye.